Hello everyone. So this is our fifth lecture of module 3, that is lecture number 3.5, module 3 fifth lecture. And today's topic is homogeneous function. Homogeneous function. In last lecture we have learned about the concepts of partial derivatives, and this topic homogeneous function, it is also depending on partial derivatives. So first of all we have to understand what is homogeneous function. Suppose we have a function f of x comma y comma z. Okay, this is any arbitrary function. Now this function will be called homogeneous if we can replace x by tx, y by ty, and z by tz. Okay, so f of tx, ty, tz. Okay, and if we can write this function f of tx, ty, tz in the form t to the power n f of x, y, z. Okay, so if we can write any function f in this form, then the function will be called homogeneous function. For example, suppose f of x comma y comma z, this is equals to, let's say I am writing xyz divided by x square plus y square plus z square. I am taking any arbitrary function. The first step is we have to replace x by tx, y by ty, and z by tz. So f of tx, ty, tz, this is equals to, so in place of x we have to write tx, so tx into ty into tz divided by t square x square plus t square y square plus t square z square. Okay, so if I simplify this, we are getting t cube into xyz divided by t square is common, x square plus y square plus z square. So we are getting t into xyz divided by x square plus y square plus z square. That means t into f of xyz, because this function, this is our f of xyz. Okay, so this is of the form t to the power n f of xyz. That means t to the power 1 into f of xyz. So we can write this function xyz by x square plus y square plus z square in this expression. Okay, that's why this function will be called homogeneous function. Okay, this function will be called homogeneous function. Now this number n, the number n is called degree of the homogeneous function. Degree of homogeneous function. Okay, so this is just a basic concept of homogeneous function. If we can write any function f in this form, f of tx, ty, tz, this is equals to t to the power n f of xyz, then the function will be called homogeneous function, and the power n, the number n belongs to real number, n belongs to R, n may be any real number. Okay, so actually not real, n must be any rational number. Okay, rational number will be the most perfect. So sorry for the disturbance. So n is any rational number, you can write n belongs to q. Clear? Now question is, here I have written 3 variables. Is it applicable for any number of variable? Yes, we can apply for any number of variable. So in general, so what will be the general form? So suppose we have a function f of x, y, z dot dot dot, any infinite number of variables. Okay, by any finite number of variables, then f of tx, ty, tz dot dot dot, this is equals to t to the power n f of x, y, z dot dot dot. If we can write in this form, then the function will be called homogeneous function. Homogeneous function with degree n. Clear? This is the basic concept. Let's solve an example. Suppose question. Suppose f of xy, this is equals to xy by x cube plus y cube. Okay, verify it is homogeneous function and find out its degree. So solution, f of tx comma ty, this is equals to tx into ty divided by t cube x cube plus t cube y cube. So this is equals to t square into xy divided by, if I take t cube common, so this will be x cube plus y cube. So this is equals to 1 by t into xy by x cube plus y cube. So you are getting t to the power minus 1 into f of xy. So obviously we can write in this form t to the power n f of xy. So this is homogeneous function. This is homogeneous function, and what is the degree? With degree minus 1. Okay, degree is minus 1. Now come to the very important topic, that is Euler's theorem. Euler's theorem, and this is very important. Okay, Euler's theorem, let's say I am writing Euler's theorem for first order. Okay, Euler's theorem first order. Remember, Euler's theorem is applicable only for homogeneous function. Clear? You cannot apply Euler's theorem for non-homogeneous function. So it is applicable only for homogeneous function. Okay. Now what is the theorem? Suppose if f x y z, right now I am writing the statement of Euler's theorem. Okay. So if f x y z be a homogeneous function of degree n, okay, then it will satisfy an equation, and the equation is x del f del x plus y del f del y plus z del f del z. This is equals to n into f of x y z. Okay, and this statement is called Euler's theorem. Okay, and here all the partial derivatives are of first order. Here del f del x, del f del y, del f del z, all the partial derivatives are of first order. That's why it is called Euler's theorem first order. Clear? Similarly, you can write Euler's theorem for second order. Euler's theorem for second order. Proof of this theorem is not important for your semester examination, so I am not completing the proof. So what will be the Euler's theorem for second order? The statement is almost same. If f of xyz be a homogeneous function of degree n, then x del x plus y del y plus z del z whole square f. This is equals to n into n minus 1 into f of xy z. Okay, and this result is known as Euler's equation for second order. Okay, or second order Euler's equation. So what is the application of Euler's theorem? Using this equation we can solve many problems. For example, let's write first question. If u equals to cos inverse x plus y divided by root x plus root y, then prove that x del u del x plus y del u del y plus half cot of u, this is equals to 0. You have to prove this. Solution. Okay, so here given that u is equals to cos inverse x plus y divided by root x plus root y, but we cannot apply Euler's theorem on this function u. Okay, actually we can apply, but the calculation will be difficult. That's why we have to change this function. How? We can write this in this form, that cos of u equals to x plus y divided by root x plus root y, and let's say this is equals to v. Okay, I am taking another function v, and vxy equals to cos u. Now we have to show that this v function, this is homogeneous function. Okay, so v tx ty, this is equals to, so this will be tx plus ty divided by root over tx root over ty. So we are getting t to the power half into x plus y divided by root x plus root y. So t to the power half into f of xy. Okay, so we can say that vxy is homogeneous function with degree half. Okay, now by Euler's theorem, we can apply Euler's theorem on v, because v is our homogeneous function. So x del v del x plus y del v del y, this is equals to n into v xy. So this implies x del del x. What is v? What is v? V is equals to cos u, na? So we can write x del del x cos of u plus y del del y cos of u. This is equals to, in n means half, so half cos of u. Okay, now del del x of cos u, derivative of cos is minus sin u, and since it is partial derivative, so minus sin u del x. Clear? So from here we can write this imply minus x sin u del x minus y sin u del y. This is equals to half cos of u. Now if I divide by sin u, so we are getting minus x del u del x minus y del u del y. This is equals to half cos u by sin u equals to cot of u. So this is equals to minus x del u del x minus y del u del y minus half cot of u equals to 0. Now if I take common minus, so x del u del x plus y del u del y plus half cot of u, this is equals to 0, hence proved. Okay, this is very important problem. Now solve another problem using the second equation. Next question. Question: if u is equals to tan inverse x cube plus y cube divided by x minus y, find the value of x square del 2u del x2 plus 2xy del 2u del x del y plus y square del 2u del y2. Okay, you have to find the value of this expression. Okay, so concept is same. First of all, you have to convert this equation, or u equals to tan inverse x cube plus y cube, this expression into tan u form. So solution, here u is equals to tan inverse x cube plus y cube divided by x minus y. Here u is not homogeneous function, because here we have tan inverse x cube plus y cube by x minus y. We cannot write u in the form of t to the power n uxy. So tan u equals to x cube plus y cube by x minus y, and let's say this is another function v x comma y. Okay, so obviously this is we have to show that this v is homogeneous. So v tx comma ty, this is equals to t cube will be common, t cube x cube plus y cube divided by t will be common, x minus y. So we are getting t square into x cube plus y cube divided by x minus y. That means t square v of xy. Okay, so v is homogeneous with degree 2. Okay, so obviously we can apply Euler's theorem. So by Euler's theorem, x del v del x plus y del v del y, this is equals to 2 degree, so 2 into v. So we are getting x del x of v equals to tan u, this v equals to tan u. So x del x of tan of u plus y del y of tan of u, this is equals to 2 tan u. Okay, so if I derive tan u, so we will get sec square u. So x sec square u del x plus y sec square u del y, this is equals to 2 tan u. Now divide by sec square u, so you will get x del x plus y del y, this is equals to 2 tan u divided by sec square u, that means cos square u. 1 by sec square u means cos square u. So we are getting this is equals to 2 sin u cos u. So x del u del x plus y del u del y, this is equals to sine 2u. Okay, let's say this is equation number 1. But question is, you have to show that this relation and all these are second order partial derivatives. Clear? Now, so now if I differentiate the equation number 1 with respect to x and with respect to y. Okay, so differentiating, first we are differentiating with respect to x. So differentiating with respect to x. Okay, or you can write differentiate equation number 1 with respect to x. So we'll get, first will be del u del x plus x del 2u del x2. Okay, plus y del 2u del x del y. Okay, is equals to sine 2u. So this will be 2 cos 2u del u del x. Clear? Now let's say this is equation number 2. Now differentiating equation 1 with respect to y. Okay, so you will get x del 2u. Okay, now del u del x with respect to y, so this will be del 2u del y del x. Okay, plus del u del y plus y del 2u del y2. So this is equals to 2 cos 2u del u del y. This is equation number 3. Okay, now anyhow we have to get the required equation. Now if we multiply the second equation by x and the third equation by y. Okay, if I multiply, because here the term is x square del 2u del x2. Okay, here we have x del 2u del x2, so we can multiply second equation by x and third equation by y. So multiplying 2 by x and 3 by y. Okay, and add them and adding them. Okay, so what you will get? So first equation by x, so this is del u del x, this is this, that will be x del u del x, and that will be y del u del y. So we are getting x del u del x plus y del u del y. Okay, this is first part, plus from here that will be x square del 2u del x2, and this will be y square del 2u del y2. So you will get x square del 2u del x2 plus y square del 2u del y2. And in this case here v is homogeneous function, and for homogeneous function these two results will be same, del 2u del x del y and del 2u del y del x. These two results will be same. So obviously if we multiply, so this will be xy del 2u del x del y, and this will be xy del 2u del xy. That means we are getting 2xy del 2u del x del y. Okay, and this is equals to what? First equation multiplied by x, second equation multiplied by y. So this is equals to 2 cos 2u x del u del x plus y del u del y. Clear? X del u del x plus y del u del y. Now what is the value of x del u del x plus y del u del y? Already given in equation number 1, sine 2u. Okay, so putting from 1, so first is x del u del x, that will be sine 2u. So sine 2u plus x square del 2u del x2 plus 2xy del 2u del x del y plus y square del 2u del y2. Okay, this is equals to 2 cos 2u into x del u del x plus y del u del y. So 2 cos 2u into sine 2u. Okay, 2 cos 2u into sine 2u. We are getting this from equation number 1, but we need only this portion, only this portion. So or x square del 2u del x2 plus 2xy del 2u del x del y plus y square del 2u del y2. This is equals to, okay, so 2 cos 2u sine 2u, this sine 2u will be on the right hand side, so minus sine 2u. So we are getting sine 2u is common, so 2 cos 2u minus 1 into sine 2u. Okay, and this is very very important result. Actually we can write this is equals to 1 minus 4 sine square u into sine 2u. How? Because here you can write as a rough work 2 cos 2u minus 1. Okay, so this is equals to cos 2 theta. We know cos 2 theta equals to cos square theta minus sine square theta. So 2 into cos square u minus sine square u minus 1 means sine square u plus cos square u. So what we are getting, 2 cos square u minus 2 sine square u minus sine square u minus cos square u. So this is equals to cos square u minus 3 sine square u. Okay, again cos square u equals to, we can write 1 minus sine square u. Okay, minus 3 sine square u. So this is equals to 1 minus 4 sine square u. Okay, that's why I have written 2 cos u minus 1 equals to 1 minus 4 sine square u. Okay, so this is the concept of Euler's theorem and homogeneous function. Now you can solve the textbook problems and the previous year question paper and your question bank. Clear? And only one topic is remaining, that is chain rule. So in next lecture I will complete the module 3 and chain rule is the last topic. Okay, thank you.